Hey, in this session I'll be talking about buffers with a pH less than 7. Calculations will be in another session, but it's important to understand what a buffer is. By definition, a buffer solution resists changes in pH during the addition of small amounts of acid or alkali. This can be, however, exceeded. The buffering capacity, as it were, can be exceeded. If you were to add too much acid or alkali, then the buffer would no longer exist. A buffer solution is a mixture of ethanoic acid and sodium ethanoate, as an example. So that's a weak acid and its conjugate base. Or to have a pH buffer of greater than 7, then you could have a weak base and its conjugate acid. So one way to achieve that would be ammonia and an ammonium ion containing compound, such as ammonium chloride. But in this session I'll be talking just about the buffer solution with a pH less than 7. So if we were to look at ethanoic acid is a weak acid. It would ionize partially to produce ethanoate and H+. And then if we were to add its conjugate base, such as the sodium ethanoate, then that would dissociate completely into ethanoate ions and produce sodium+. The ethanoic acid is sometimes represented as HA, HX, or HY. They all generally mean the same thing, as being a weak acid. So in terms of amounts, our HA, the weak acid, would ionize partially, so therefore it would decrease by a small amount if we were to put it in solution to produce the same amount of H+ and A-, in this case the CH3COO ethanoate ions. So therefore you can say Ka is equal to H+ times A- over HA, the amount of product compared to the reactant. Because they're the same, we can therefore say H+ squared over HA is Ka. If you wanted H+, then you could then, as concentration, square root Ka times HA concentration. We've made some assumptions here, actually, in that the HA has actually decreased, so therefore that value should have gone down. But we don't care about that, so therefore, to make things simpler, we just assume that HA concentration has not changed. So that is one of the assumptions. If you were to get asked, what is the assumption you have made with this? A- will also be the same as H+, when in reality the H+ would have been slightly different because we have ignored the dissociation of water that would have produced H+ and OH- as well. So we're assuming that the H+ only has come from HA, and even though HA has decreased by a small amount, we're assuming that is the same value as well. So these are some assumptions that we make with the weak acid dissociation in general. But in a buffer solution, it's slightly different. We have this going on, as described earlier, so the HA dissociates to produce the same amount of H+ and A-. But because we have the sodium ethanoate in there as well, this is ionic and therefore 100% ionizes. So whatever amount we had of that to begin with would completely go and produce 1 and 100% conversion of the ethanoate and sodium ions. In this case are just simply spectators. The sodium ion we don't really care about. So all of the sodium ethanoate is no longer associated, it is all dissociated, and that's going to therefore mean that when we mix these together, when we were to say before Ka was equal to H+ squared over HA, we can no longer assume that because the A- therefore would add to the existing A- that was produced by the weak acid, and therefore we can no longer assume that mathematical relationship. We would therefore have to treat them as separate entities, so to speak, and therefore if we wanted to work out the H+ concentration, we would have to rearrange it. We can no longer assume that, therefore, and we'll have to rearrange it to be like this instead, because we are no longer able to say that H+ is not the same as A-, so we can't say Ka is equal to H+ squared over HA, and we therefore can't say H+ concentration is equal to the square root of Ka times HA. And that's what you would normally use in standard Ka calculations. But whenever the word says buffer, or you were to be told that you have sodium ethanoate in there, for example, with a weak acid and its conjugate base, making ethanoate and sodium ions, then you can no longer assume those relationships, and therefore you have to use H+ equals Ka times HA over A- if you wanted to work out the H+ concentration. Whenever you get a question that tells you, therefore, say sodium ethanoate, you have to assume that it is the concentration of A-. And we have therefore made another assumption, and we've assumed that the A- in which it's dissociated is not going to affect the actual total there, so we've ignored it. So that's another assumption we made there. The large reservoir of HA and A minus that is produced is now what we would describe as being the buffer solution that has now been prepared. So if we were to add hydrochloric acid, which is a strong acid, to our buffer mixture, you could be asked to describe what happens to this. So initially, there would be an increase in H+. So if you were to add H+ as hydrochloric acid, that would increase slightly. Therefore, our equilibrium has therefore been disrupted in terms of pH. It's no longer constant. So to bring it back, you could argue Le Chatelier's principle here. So we want to remove that amount of H+ that we have added. To remove that H+, we need to understand what will react with that H+. We have A- in there, quite a lot of it. And so it's going to bump into that, so to speak, collide into it. And when it does, it's going to decrease and react in the same ratio as it would do in molar amounts. So in this case, it will decrease by that amount, and it will produce HA, which will increase slightly by a small amount as well. And so, not to scale, but HA would relatively be similar to A-, but the important thing here is the H+ concentration and thus pH has remained approximately constant. There'll be a slight variation in the change of pH, but the H+ ion concentration is resisting the changes, the drastic changes we added. And so we would argue that the position of equilibrium moved left to produce more HA, thus decreasing the amount of H+. A- decreased by a small amount as well, but because there's so much of it, it's not really going to make much of a difference because it is virtually constant. It's got a large reservoir of the A-. So the H+ and pH remains approximately constant, and you can argue to say HA and A- ratio does not change by much. If you were to add hydroxide, such as sodium hydroxide with an alkali, as an alkali, to the buffer mixture, you could then again be asked to describe what happens qualitatively. So you could say that the hydroxide you've added will react with the weak acid, and you should understand this from standard acid-base reactions. So weak acid plus sodium hydroxide could make sodium FNO8 and water. That would therefore save, as it were, and prevent it from reacting it with the H+ and stopping it from removing the H+, and therefore it's going to again remain approximately constant. And you have a large reservoir of HA and A- still, and so your buffer resists change through the H+. So the hydroxide you've added is going to bump into HA and react with it instead of reacting with your H+. There's quite a lot of it, so it will do that probably most likely. You could argue instead that the hydroxide ions reacts with the H+, which would decrease it by a little amount to make water. So H+ plus OH- would make water, and therefore that would decrease. So I won't show you by animation, but in order to return it back to normal, the position would have to move right to return the H+ back to what it was to keep the pH approximately constant. So hopefully that helps a little bit in understanding the qualitative aspect to how a buffer resists changes in pH. I will try to make another video on calculations. For more chemistry support, do check out the other videos, and hopefully I'll be able to get some more videos out to you soon.